I am Dr. Gaurav Sinha, Professor, IIMT College of Engineering, and I'm going to teach you the subject Optical Communication Fiber Technology. And optical communication subject is present in 7th semester of AKTU syllabus in EC branch. So all those students who are in EC branch currently studying in 7th semester, they can view the lectures and they can follow my lectures on YouTube. So students, let's start the first lecture of optical communication technology. So before I start optical communication, I will explain you what is the use and what is the importance of optical fiber communication. We know that optical fiber communication is extensively used nowadays in the whole world. If we talk about internet access, then many of you might be having this optical fiber cable laid in your society or nearby areas, and you might be accessing internet through optical fiber cables. Why we are using optical fiber communication for the data communication, for internet access? Just because the bandwidth is very high and the speed of signal transmission signaling is very high. If I talk about the signaling rate, it's very high because pulse repetition frequency is in GBps, that is gigabits per second. If I can compare this optical communication with conventional communication systems like digital communication, which we were using electrical signals, the speed was in maybe 10 Mbps or 100 Mbps. But in optical fiber cables, when we transmit optical pulses, the speed is in GBps and sometimes in TBps, terabits per second. So that is the main advantage of optical fiber communication systems, that the bandwidth is very high, and that is why we get a very high signaling rate in optical fiber communication. Most of the developments in optical fiber communication has happened after 1958, when the lasers were discovered. So as we all know that laser is a source of light, and it is a source which is highly monochromatic and coherent and also very much intense. So all these qualities are there in the laser sources of light. So it has tremendous bandwidth also. You might have studied about helium neon lasers in physics. It has a frequency of 4.7 into 10 raised to the power 14 hertz. So it's a very high frequency, 10 raised to the power 14 hertz. If I say, it's a very high frequency, and if even if I take 1% of this 10 raised to the power 14 hertz frequency, then 1% of this comes out to be 4,700 gigahertz. So that much bandwidth is sufficient to carry approximately 1 million television channels. So from this you can get an idea how much efficient is this optical source are there, how much efficient is the laser as an optical source. Okay, if I talk about laser beam is confined to a transmission channel by lenses which are spaced at some specific intervals. So in conventional communication systems, we transmit electrical signals, whereas in optical communication systems, we transmit optical signals, or you can say we transmit light as a signal. We use light as a signal, and the pulse which we transmit, those are optical pulses. If I talk about the channel which we use in optical communication, the channel is a glass fiber. The fiber consists of glass core at the center, and the glass core is surrounded by cladding of slightly lower refractive index as compared to that of core. So if I explain you the structure, then structure is like that. There are three different you can say partitions. First is the central part, that is core, having very high refractive index. Then the outer part of the core is called as cladding, having slightly lesser refractive index. And then there is third outermost covering, which we call as jacket, which is used to protect the core and cladding. So the cable has three sections, three parts. Central part is core, then middle part is cladding, and the outermost part is jacket. It simply act as a dielectric waveguide. By mid 1980s, the fiber with guaranteed attenuation of less than 0.4 decibel per kilometer at 1.3 micrometer wavelength was commercially obtained. So it started in 1980s, mid of 1980s, when the first commercial optical fiber was launched, and having very less attenuation, that is 0.4 decibel per kilometer, and the wavelength at which this fiber operated was 1.3 micrometer. Those days the optical source which was used was gallium aluminum arsenic, and some detectors were used, which were semiconductor detectors made of silicon. So in the this technology evolved or emerged in the decade of 80s. In 80s, the fiber had replaced copper nearly in all new trunks of capacity greater than 8 Mbps. So by the 1980s, end of 1980s, optical fiber had replaced the copper wires in the capacity of more than 8 Mbps data speed. Now let's see the definition. I will share my screen with you, and let's see the definition of optical communication system. So here we can see the definition of optical communication system. It is propagation of light through dielectric waveguides. So in optical, as I said, in optical communication, light travels through the channel. In any communication system, we have three basic parts, three basic blocks. One is known as transmitter, second is channel, and third is receiver. So here in optical communication also, we have transmitter, channel, and receiver. In if I talk about transmitter, then it comprises of the source which will generate the signal to be transmitted. In transmitter, we have optical source. Optical source are like lasers, laser diodes, or light emitting diodes, LEDs. So we can use these as optical sources. In channel part, we always use optical fiber cables, which is made up of glass, as I have already explained, and the covering of plastic covering, which is known as cladding, and then outermost jacket, which protects the core and cladding. So it is the propagation of light through dielectric waveguides. So basically it is a dielectric waveguide having dual, you can say, the polarity, and the propagation of light is through based on the principle of total internal reflection. So whatever light which is launched into the optical fiber, it travels throughout the fiber through total internal reflections. It is every time it is reflected by the interface of core and cladding. So it is reflected totally, and then it propagates towards the receiver, and it is finally received at the receiver, which is generally a photodetector diode, and then it is finally converted into the electrical signals. Now it is extensively used as a transmission line. If I talk about optical fibers, it is basically used as a transmission line between the terrestrial hardwired systems. So whatever terrestrial hardwired systems are there, they all are connected with the help of optical fiber cables. And secondly, it is used for the transmission of data. So transmission of data from point to point location. Third point is it has tremendous bandwidth. It has tremendous bandwidth. and very high information carrying capacity. Conventional communication system always have limitations related to bandwidth because their carrier frequency is low. But in optical communication, the frequency is very high. As I have already explained, we use laser sources in optical communication, and laser source produce light of very high bandwidth, 10 raised to the power 14 hertz, you can say, frequency. Optical signals are generated using laser technology, laser optical sources. So it has a tremendous bandwidth, and since it has very high carrier frequency and very high bandwidth, so we have very high information carrying capacity. So when we transmit data from one point to another point, so obviously we need a very high data rate transmission, very high data transmission rate. So for that we need bandwidth, and since we have tremendous bandwidth, so obviously the data transmission rate is very high, because both are directly proportional to each other. Every time the transmission of data transmission rate depends upon the bandwidth available for the signal. Now, if we talk about evolution of optical fiber cables, then we can divide it into generations. So it all started from the first generation, and then it gradually moved on to second generation, then third generation, fourth generation, and fifth generation. So currently we have fifth generation. We are in fifth generation. So in first generation, if I talk about the bit rate was 45 Mbps, and repeater spacing, as we know that the signal is being attenuated, and after certain distance the signal vanishes and the signal may die. So after a particular distance we need repeaters which will regenerate the signal, and then again the signal will be transmitted further. So after a certain distance we need repeaters. So here in the first generation repeater spacing was 10 kilometer, and the wavelength of the light signal was 0.8 micrometer, right? So this was about the first generation. Now we will see in second generation what was the bit rate and repeater frequency. In second generation, bit rate is 100 Mbps. So it is 100 Mbps, and the repeater spacing is also increased 50 kilometer, and the wavelength of the signal was 1.3 micrometer. So you can see that the bit rate means number of bits transmitted per second. So here we can see 100 megabits was transmitted in 1 second. So it's quite high in the second generation. In the first generation it was simply 45 Mbps, so it was quite low, whereas in second generation the bit rate increased to 100 Mbps. Repeater spacing, earlier it was 10 kilometer in first generation. In this generation the repeater spacing is 50 kilometer, and the wavelength is 1.3 micrometer. Next is the third generation of optical fiber communication. In the third generation, bit rate further increased. It was further increased and it became 10 Gbps. So here Gbps refers to gigabits per second. So 10 gigabits can be transmitted per second. So that is the capability of that third generation optical systems, optical communication systems. If I talk about repeater spacing, then in third generation repeater spacing was 100 kilometer. So there was, you can say, less attenuation in the signal in the third generation as compared to previous two generations. The third generation had very less attenuation of the optical signal. Wavelength of the third generation signal was 1.55 micrometer. So this is the optical wavelength used in the third generation. Then we will move on to fourth generation. In the fourth generation of optical fiber communication, bitrate was further increased to 10 Tbps. So that is terabits per second. Okay, so here 10 terabits, okay, can be transmitted in 1 second, and the repeater spacing is, the systems used in fourth generation were having repeater spacing 10,000 kilometer. So it shows ki how many, you can say, how less was the attenuation in the signal in the fourth generation. So the drastical improvements are there. The attenuation has reduced drastically, and that's why the spacing between the repeater has increased drastically. In the third generation, it was just 100 kilometer. In the fourth generation systems, the repeater spacing is now 10,000 kilometer, and the operating wavelength is 1.62 micrometer. So this is the wavelength in the fourth generation. Now let's see the fifth generation. So in fifth generation, the bitrate further escalated and it became 40 to 160 Tbps. To 160 terabits per second. So it means that 160 terabits can be transmitted in 1 second, and the repeater distance further increased to 35,000 kilometers. So that was the distance between the two repeater stations, which are meant for regenerating the optical signal because of attenuation. So it basically means that distance has increased between the two repeater stations. So the reason behind is that the attenuation in the signal has drastically reduced. So as I told you in the beginning, in 1980s, the attenuation was 0.4 dB per kilometer. So it has further reduced. Okay, so whatever attenuation that is below 1 dB, so that's good for the transmission of the signal. The operating wavelength in fifth generation was 1.5 micrometer. So this was the wavelength at which the signal operated, optical signal operated. In the fifth generation, one important point is there. Fifth generation uses Raman amplification technique. Raman amplification technique. And also it uses optical solitons. So this is the technology being used in the fifth generation optical communication systems, Raman amplification technique and optical solitons. Now, as we have seen all the generations, Now we will move on to the importance and what is the need of optical communication, or maybe uh, why we need optical communication in our life. Okay, so there are few points I have written here. First is the transmission loss. See, there is a need of low transmission loss in any communication system. Any communication system, there is a need of low transmission loss. And since optical communication offers very low loss, okay, and attenuation is very low in optical communication systems, so that is why we need optical communication systems. Second thing is there is a need of compact, very small size, you can say, transmitters and receivers. And in optical fiber communication, you might be using modem in your house, okay, and those who are having that wideband connections, okay, broadband connections, so they might be using those modems, and you might have observed that the size is very small. So the systems, transmitters, receivers, in case of optical communication, the size is very small. So there is need there is a need of compact transmitter and receiver. Third thing is long span. We want that the transmission of signal uh, should be of long span, means there should not be uh, joints between the you can say channels. It should be a long channel, and we should be able to transmit a signal to long distances. So in this optical communication there is advantage that we have increased span of transmission. In the beginning, there was a big problem. We could not have long length of fibers. We used to join two sections of optical fiber cables, but now that problem has been resolved, and we have long sections of optical fibers, and we can transmit signal to longer distances. So there was a need. There is a need of increased span of transmission. If I talk about data rate, there is a need of increased uh, bit rate for data. We all know that there is always a desire of high speed of internet, so that is high bit rate. Okay, so there is a need of increased bit rate for data. So bit rate means transmission bit rate. So how many bits you are transmitting in 1 second. So that is called as bit rate. So everybody wants a high speed internet. Okay, so that is why optical fiber communication is the solution for high speed internet access. It offers you a very high bit rate. Now we will move on to the block diagram of optical communication system. So here you can see this is a block diagram of optical communication system, and in just like in any other conventional communication system, optical communication also have three basic blocks. First is the transmitter, second is the channel, and third is the receiver. But there are few more components which are used in optical communication. Basic blocks are three: transmitter, and then you have channel, and then you have receiver. Transmitter is used to process, or you can say used to modulate the signal, okay, make it suitable for the transmission. So that is the work of the transmitter. It makes your signal more usable, means more transmittable. It will sometimes the channel, you know, the bandwidth of the channel is different. So if the signal bandwidth does not matches with the channel bandwidth, then it's difficult to transmit the signal. So the purpose of transmitter is to match the characteristics, match the bandwidth of the signal with the channel. In analog communication also and digital communication also, we use different type of modulators. Those modulators basically they use some carrier signals, and those carrier signals are used to increase the frequency or to match the frequency of the message signal with the bandwidth of the channel. So the whole process is called as modulation. So here also we have transmitter. You can see here in the diagram, block diagram. So the block diagram we will see in detail in the next lecture. Just to summarize, I would say that block diagram has components like transmitter, and you have connectors, and here you can see there is a component which is known as splice. So this is splices, and this is connector, which is you can say temporary connections, whereas splice, this is usually permanent connection. So this is permanent. Splice is a permanent, whereas these connectors, these are demountable. They are demountable connections. And then further you can see there are some optical couplers. Then there is a regenerator. You can see here there is a regenerator. Okay, and then again splices, optical amplifiers. So like this you can see here different parts. Then you have amplifiers, detectors, signal restorer. So that is the receiver of the optical communication. So we will see in detail this block diagram in the next lecture. So let me end lecture here. Thank you.